Okay guys, so this is a video about variable acceleration, which seems like a rather odd thing to do at this time of year. Mechanics is long behind us, but you've got to think in these terms that we're going to be testing you guys on that in the second to last week before the end of the year. And mechanics has been a little while, so it's worthwhile just recapping some of the basic concepts. Now, in the past we've looked at SUVAT, not actually with me on a video, oddly enough, but you will have spent considerable time doing it. And SUVAT rests on the idea that acceleration is constant. Where you change your acceleration, you do a whole new SUVAT. But what if acceleration wasn't constant? What if acceleration was actually a variable? Well, we sort of can deal with that. We confine it to a certain set of parameters, but we do mess around with variable acceleration, and let us talk about the context in which we do. We generally talk about particles moving along what they describe as a horizontal plane. From the diagram you've got below, I want you to kind of visualize that horizontal plane as a number line, because that's pretty much what it is in this particular case. And at different times, whatever the formula or whatever the function s of t gives us, s remember means displacement, you substitute the value of t in there and it tells you where things are. So when t equals 0, the whole thing is 0. When t equals 1, you've got 1 cubed plus 3t squared, which is 1 plus 3, which is 4. At minus 1, which seems counterintuitive, going back in time, but just go with it, you've got minus 1 cubed, minus 1, plus 3, and that's positive 2. Now, I apologise for the drawing, because it implies almost that there is a vertical component to this, and there really isn't. We're moving up and down on a horizontal plane. That's all that's happening there. It's two-dimensional completely. We are not doing anything in 3D. So, I think from that little introduction, we've got some quite useful basic ideas. We're moving up, well, not moving up and down at all, we're moving left and right on the plane. We've got something called s of t, where t is time, and s is displacement, so the function of displacement is given in terms of time, and we can use that to find out where we are at any given time. Okay, all well and good. But what has that got to do with acceleration? Well, you're about to find out, aren't you? So what I've chosen to do here is kind of illustrate how displacement, velocity, and acceleration work through an actual physical example. And the way they work is that if you differentiate the displacement function, you get the velocity function. And if you differentiate the velocity function, you get the acceleration function. So every step you're differentiating one step down, one step down. This is not as counterintuitive as it may seem, because let's take velocity and acceleration. Acceleration is the rate of change of velocity, isn't it? It's how much your velocity is changing. And what method gives you rate of change? Nothing but differentiation. So really, it makes absolute sense that if you differentiate the velocity, you'd get the acceleration. Similarly for displacement to velocity. If you differentiate, if you look at the change in displacement, your rate of change of displacement, you've got your velocity, how fast are you travelling. It makes absolute sense that if you differentiate your displacement function, you get a velocity function. It's not some kind of magic or some kind of like, oh wow, this is just the thing that happens because mathematics miracles. It's completely rational, and it coincides with the things that you've learned about differentiation, namely that it tells you the rate of change of a function. So you differentiate displacement to get velocity, you differentiate velocity to get acceleration. That's hopefully pretty self-explanatory. Okay? What happens with integration? Well, we'll come on to that in just a moment. Okay, so you're probably introduced to integration as the antiderivative. Basically, it's the opposite of differentiation. So your kind of suspicion about this is true. Integrating takes you back up to where you started. But there's one caveat, and it's always the same caveat with integration being used as inverse of differentiation. There are constants, yeah? The constant of integration. So if you look so we've looked at this function 12t, I've just made that up. Integrate that, you get 6t squared plus c. Integrate it a second time, even the constant itself gets raised to become ct, and now you've got a second constant d, so there's two constants involved there. That's quite annoying. So how do we deal with that problem? We are generally in questions given some values that we can substitute in to find c and d, and you should do that where they give them to you in order to remove the constant or work out what the constant actually is. So that's how you deal with the constant. Now that's pretty much all of that chapter actually. There's not a lot in it if you understand that differentiating from displacement gives you velocity, differentiating velocity gives you acceleration, and integrating takes you back the other way. And that's pretty much all you need to know, other than you're dealing with potentially constants. So I hope that made sense. And that's a whole chapter in 5 minutes, which is pretty damn good. I'll leave it there.